Next chapter, sequences and series. Sequences. A sequence is a pattern of numbers in a definite order. Consider these two sequences. Each number in a sequence is called a term. In the first sequence, the first term is 1, and in the second sequence, the third term is 18. For a pattern to qualify as a sequence, it must be governed by a rule that is consistent throughout the sequence. For the first sequence, the rule is adding 4 to each term to obtain the next term. And so 1 plus 4 is 5, 5 plus 4 is 9, 9 plus 4 is 13, and so on and so on. For the second sequence, the rule is multiplying each term by 3 to obtain the next term. So 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, and so on and so on. When the rule governing a sequence is given, we can determine the terms of the sequence. The position of a term in a sequence is represented by n. For example, in our pattern, 13 is the fourth term, and so n for 13 is 4. 21 is the sixth term in the second sequence, and so n is 6. For example, write the first 5 terms of a sequence governed by the formula n squared plus 2. For the first term, n is 1, therefore we have 1 squared plus 2, giving us 3. The second term, n is 2, and so 2 squared plus 2 is equal to 6. Third term, n is 3, and so 3 squared plus 2 is 11. Fourth term, n is 4, and so 4 squared plus 2 gives us 18. And finally, fifth term, n is 5, and so 5 squared plus 2 is 27. The sequence is therefore 3, 6, 11, 18, 27. There are two types of sequences: arithmetic and geometric sequences. Arithmetic sequence. An arithmetic sequence is one in which the terms differ by a fixed value. In our cases, the first sequence 1, 5, 9, 13, 17, and 21, the consecutive terms differ by a fixed value 4. So this is an arithmetic sequence. The fixed value is called the common difference, D. The common difference could also be a negative. For example, in this sequence, the common difference here is negative 3. The first term is represented by A. So in the first sequence, A is equal to 1, and in the second sequence, A is 6. Because in an arithmetic sequence the terms differ by D, then the first term is A. The second term is obtained by adding D to the first term, and so we shall have A plus D. The third term is obtained by adding D to the second term, and so we shall have A plus D plus D, giving us A plus 2D. The fourth term is obtained by adding D to the third term, and so we shall have A plus 2D plus D, giving us A plus 3D. The fifth term is obtained by adding D to the fourth term, and so we shall have A plus 3D plus D, giving us A plus 4D. You will observe that the coefficient of D in each case is 1 less the position of the term, and so if you wanted the 10th term, it will be A plus 9D. And so given that the position of a term is represented by n, then the nth term of an arithmetic sequence will be given by nth term is equal to A plus n minus 1 times D. This is the general rule governing all the arithmetic sequences.
For
Example, find the 10th term in the following sequences. For the first one, A is 1, D is equal to 4. We are looking for the 10th term, and therefore n is equal to 10. And so we shall have 1 plus 10 minus 1 times 4. That gives us 1 plus 10 minus 1 is 9 times 4 is 36. And so the answer is 37. For the second one, A is 6, D is minus 3, and n is 10. And so we shall have 6 plus 10 minus 1 times minus 3. That gives us 6 plus 10 minus 1 is 9 times minus 3 is minus 27. And the answer is minus 21. Another example, find the number of terms in this sequence: 4, 7, 10, 13, all the way to the last term, 61. In this sequence, we have the first term 4, and we can see the common difference is 3. We are also given the last term of this sequence to be 61. So we need to find 61 is position what? So we are looking for n. We can say the nth term is 61. We equate A plus n minus 1 times D should give us 61. So 4 plus n minus 1 times 3 is equal to 61. 4 plus, open the bracket, 3n minus 3 is equal to 61. 3n is 60 and n is equal to 20. So 61 is the 20th term, and being the last one, it means there are 20 terms in this sequence. Another example, the second and fourth terms of an arithmetic sequence are 6 and 12. Find the first term and the common difference. Second term will be given by A plus D, and that is equal to 6. The fourth term will be given by A plus 3D, and that is equal to 12. We solve the two simultaneously. We can do that by subtraction. We eliminate A. If we do that, A minus A is 0, D minus 3D is minus 2D, 6 minus 12 is minus 6, and therefore D is equal to 3. Substituting D in any one of the equations, we do it in the first one. A plus 3 should be equal to 6, and therefore A is equal to 3. Last example, an employee has a starting salary of 10,000 with an annual increment of 2,500. Find the salary at the end of the 5th year. In this case, A is the starting salary and is 10,000. D is the annual increment and it is 2,500. N is the number of years and it is 5. So we have 10,000 plus 5 minus 1 times 2,500. That gives us 10,000 plus 5 minus 1 is 4 times 2,500 is 10,000. And so the answer is 20,000. Next, series. A series is the sum of the terms in a sequence. The series for an arithmetic sequence is called an arithmetic progression, or AP. For our case, the AP is the sum of these terms. if we add the first 4 terms, then the AP represented by S4 will be equal to 1 plus 5 plus 9 plus 13, giving us 28. And because sequences continue to infinity, we must be given the number of terms to add. For example, the first 10 terms, the first 100 terms, and so forth and so forth. In general, the sum of the first n terms of an AP is given by Sn is equal to a half n into 2a plus n minus 1 times d. For example, in our case, we can find the first 100 terms. A is 1, D is 4, and N is 100. And so S100 is equal to a half times 100 into 2 times 1 plus 100 minus 1 times 4. So we get 50 into 2 plus 99 times 4. We get 50 times 398. And that gives us 19,900. Another example, find the sum of the following series. From this, we can see A is 3 and we can tell D is 2. Also, the nth term is 71, so we need to find N. We know that the nth term is given by A plus n minus 1 times D. So 3 plus n minus 1 times 2 is equal to 71. 3 plus 2n minus 2 is equal to 71, 2n is equal to 70, and n is 35. So we are finding the sum of the first 35 terms. S35 is equal to a half times 35 into 2 times 3 plus 35 minus 1 times 2. That gives us 17.5 into 6 plus 68. That gives us 17.5 times 74, giving us 1,295. Last example, find the sum of all odd numbers between 10 and 50. The first thing to know is what odd numbers are. From 10 to 50, the first odd number is 11 and the last one is 49. Also, consecutive odd numbers differ by 2. And so we can form a sequence 11, 13, 15, 17, all the way to 49. A, the first term is 11. D is 2. The nth term is 49. So we find how many terms are in this sequence if the last one is 49. Nth term is given by A plus n minus 1 times D. 11 plus n minus 1 times 2 will give us 49. 11 plus 2n minus 2 is 49. 2n is 40 and n is 20. And so between 10 and 50, there are 20 odd numbers. So S20 is equal to a half times 20 into 2 times 11 plus 20 minus 1 times 2. That gives us 10 into 22 plus 38. That gives us 10 times 60, giving us 600. Moving on, next, geometric sequence. Now consider the sequence we had previously. The rule we said is multiplying each term by 3 to obtain the next term. So 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54, and on and on. This common multiplier is called the common ratio, R, and the sequence is called a geometric sequence. By definition, a geometric sequence is one in which consecutive terms have a common ratio. The ratio could be a fraction or even a negative number. For example, in this sequence, the common ratio is -1/2. The first term in a geometric sequence is still A. And because the consecutive terms have a common ratio, then the first term is equal to A. The second term is obtained by multiplying the first term by R, that is A times R, giving us AR. The third term is obtained by multiplying the second term by R, so we have AR times R, giving us AR squared. The fourth term is obtained by multiplying the third term by R, so we have AR squared times R, giving us AR cubed. The fifth term is obtained by multiplying the fourth term by R, so we have AR cubed times R, giving us AR raised to power 4. You should realize that the power of R in each case is 1 less the position of the term. And so if you wanted the 10th term, it will be given by AR raised to power 9. In general, the nth term of a geometric sequence is given by nth term is equal to A R raised to power n minus 1. For example, determine the 6th term in this sequence. In this sequence, we can see A is 1, and we can also see that R is 4. N is 6 because we are looking for the 6th term. And so we shall have 1 times 4 raised to power 5, giving us 1024. Note that in a geometric sequence, R cannot be 1, neither can it be 0. Geometric progression. The sum of a definite number of terms of a geometric sequence is called a geometric progression, or GP. The sum of the first n terms of a GP is given by Sn is equal to A into 1 minus R raised to n over 1 minus R when R is less than 1. And A into R raised to power n minus 1, everything over R minus 1 in cases where R is greater than 1. For example, find the sum of the first 6 terms of the following series. In this sequence, A is 2, R is 3, and n is 6 because we are looking for the 6th term. In this sequence, R is greater than 1. So we apply the second formula. S6 is equal to 2 into 3 raised to power 6 minus 1 over 3 minus 1. That gives us 2 into 728 over 2. The 2 cancel out and we get 728. Another example. The 4th and the 7th terms of a GP are 36 and 288 respectively. Find the first term, the common ratio, and the sum of the first 10. In our solution, the 4th term is given by AR raised to power 3, and that is equal to 36. The 7th term is given by AR raised to power 6, and that is equal to 288. And so the 7th term over the 4th term should give us 288 over 36. If we divide that, AR raised to power 6 over AR raised to power 3 should be equal to 288 over 36. A cancels out r raised to power 6 over r raised to power 3, we simply subtract the powers. So r raised to power 3 is equal to 8. Finding the cube root, r is 2. To find a, we substitute in any of the equations. We use the first one, it's easier. A times r raised to power 3 is 36. We already found r is 2, therefore a times 2 cubed is 36. If you divide that, you'd get a is 4.5. As 10 is equal to 4.5 into 2 raised to power 10 minus 1 over 2 minus 1. Last example. Given that 75 plus x plus 12 is a geometric progression, find the possible values of x. Now, we've said that in a GP, consecutive terms differ by a common ratio. This sequence basically is 75, x, 12, and on and on. The first term is 75, the second term is x, the third term is 12, and so on and so on. In a GP, the second term divided by the first term should be equal to the third term over the second term, and both of them are equal to r. And so we can say AR, that is the second term, over A, the first term, is equal to r. Also, AR squared, the third term, over AR, the second term, is equal to r, the common ratio. It therefore means that AR over A should be equal to AR squared over AR, because both of them are equal to r. In that case, we can say that x over 75 is equal to r, and also 12 over x is equal to r. That means that x over 75 should be equal to 12 over x. Cross multiplication, x squared is 900 and x is plus or minus 30.
The second thing I love about math is it's a puzzle solving kind of, if I can figure it out, and the joy of figuring it out, the kind of sense of accomplishment, the sense of excitement when you get it, the challenge of trying to get it. It's that puzzle solving kind of thing that I really, really like.